Welcome to Graphing Notes Part 3. We're going to look at motion maps initially, and the first example is going to be of an object that is moving fast, but then slowing down, and then finally stops, and then turns around and goes in the other direction faster and faster. So let's draw the motion map for this. We're going to have it go to the right, and so we start with the dot on the end, and then a really big arrow, because it's going fast initially. And then this next arrow is going to be slightly shorter. And remember, these arrows represent the velocity. So these arrows going to the right tell me it's going to the right, and then the length of the arrow tells me the relative speed of the object. So as these arrows get shorter and shorter, we know the object must be getting slower and slower. So we'll have it stop there. And then we'll have it turn around. And you can stack these going up, you can stack these going down. I'm going to stack it going down. There's no significance on being above or below the line, but I just wanted to, let's get it right below it. Over here. There we go. So now it's going to go back in the other direction. And then again, it's going to speed up and go faster and faster in the other direction. Maybe that one was a little too much of an increase. It's going to speed up a little bit every time. And we know it's going faster and faster because the arrows are getting longer and longer. So here's our motion map. And we want to say here that t equals 0 seconds. Otherwise, it's not terribly clear where we're starting. And now the next thing we're going to do is we're going to draw acceleration vectors on here. And this arrow represents, that we see that's already drawn, represents the velocity. So when it's going to the right and it's slowing down, it's getting slower and slower and slower initially. So the acceleration must be going against the velocity. It's working against it. So for the acceleration arrow, let's use a slightly bigger, there we go, do it in green, and it must be going back this way to the left because it's working against the velocity. And we said it was a constant acceleration. So the constant acceleration, those arrows must be exactly the same for each of these. So each second, and I probably didn't draw this to scale, but ideally each second the arrow would be the same, the red arrow would get shorter by the same amount. And so because it's going to the right, the object's moving to the right and slowing down, the acceleration must be to the left. It's working against it. So those arrows are sort of pointing against each other. Now at the bottom here, the object turns around and goes to the left and goes faster and faster. So it's going faster and faster. The acceleration arrows must be helping the velocity arrows to get longer. Initially, they were making the velocity arrows get shorter. Now they're making it get longer. So the acceleration arrow still points to the left. And it's the same length as before because we have a constant acceleration. And the red arrows should be, and I didn't do a very good job of this, but the red arrows should be getting longer by the same amount every time. So you'll notice here that these acceleration arrows are exactly the same everywhere on here. This one looks a little long, but we'll cheat and just say, put tick marks on there, say, hey, even though I didn't draw these necessarily to scale, they should be the same length the entire time. We can go back and make this one smaller if we really want to. There we go. So this is an example of a constant acceleration while it's going in two different directions, which I think a lot of people confuses people because we think constant acceleration, we either think speeding up or slowing down, but in this case it's slowing down and then speeding up. The entire time it has the same acceleration. Next one we'll look at is slowing down and then speeding up, and we'll see if the acceleration is the same on that one. So let's zoom in here and we will say this is where we're starting. This is t equals 0 seconds. And it's slowing down and then speeding up. So maybe this is somebody going towards a red light and they see the red light and so they start to slow down. And they're going slower and slower and slower. They're still going in the positive direction, going to the right. and maybe they get to a point where they stop for an instant there, and then they're going to continue on. And I really shouldn't draw another arrow like this because then it wasn't moving and then it got to there. But also we could have just missed that. These are only 1 second intervals, so not a big deal. These motion maps are supposed to give us an idea, not going to be perfect. So now it's going to be going faster and faster and faster as the arrows get longer and longer. Notice it's going the same direction the entire time. The velocity's always to the right. So now let's go through and draw the acceleration vectors. So if I'm slowing down, my acceleration vector must be working against my velocity vector. So just like before, let's draw it shorter this time. Just like before, so we'll label it acceleration. We have an acceleration vector going to the left. It's going against the velocity vectors in order to slow it down. So we're slowing down, going slower and slower and slower. And we're going to say this is a constant acceleration. I do a terrible job of this. These need to be longer. Oops. And the acceleration can be, those arrows can be longer than the velocity vectors. There's no rule against that. It just sometimes makes it a little harder to draw and to fit everything in there. Anyway, all those acceleration arrows are supposed to be exactly the same size. Now what happens here, now we're speeding up. So the velocity is getting helped by the acceleration arrow. So the acceleration actually changes direction and is now going to the right. And again, we're going to say this was the same magnitude of acceleration the entire time, so all our arrows are going to be the same. So one thing that's kind of funky in here is slowing down and speeding up, you actually change the direction of your acceleration. But slowing down and speeding up in the opposite and then turning around, you have the same direction of acceleration. So just something to think about there. There's motion maps, and now let's go down to the second part of our notes, which is the velocity versus time graph going to an acceleration versus time graph. So for an acceleration versus time graph, we're only going to deal with horizontal piecewise graphs in this class. Outside of class, in other physics classes, just in actual motion, they're not just horizontal piecewise, but we're going to model it as horizontal piecewise because it's a pretty good approximation and it keeps it simple. So let's do this one first. This will be motion A. To get the acceleration, we are just going to look at the slope. So we're going to look at the slope here. Remember, slope is the change in velocity over the change in time, and that equals the acceleration. So this is for initially here, whoops, acceleration. Line A rather than line B. So line A has a negative constant slope. So all we do is we go over here to the acceleration versus time graph. We say, oh, okay, you need to have a negative constant slope. So that would be A. For B, B has a positive constant slope. So, and it looks like the magnitude of the slope is a little less steep than the other one. So here's B. There's a positive constant slope. Acceleration versus time graph is done for both of those. Now let's go on to the position versus time graph. If we want to go from position versus time to acceleration versus time, it's all about the concavity. Here's the shortcut. So this is concave up. So concave up, that means positive acceleration. Concave up means if it's like a bowl of soup, it can hold the bowl of soup. Concave down, it's like an upside down bowl. Maybe it's a hill. Concave down is going to be a negative acceleration. How do we know that? How do I get that shortcut? Well, if we look here, initially we are going fast in a negative direction, but we're slowing down. So whenever we're slowing down, the direction of the acceleration will always be opposite the direction of our velocity. I think that's important enough to write down. Let's write that up here, kind of in the middle. So when slowing down, direction of acceleration, or let's say of the acceleration vector, just to make sure what we're talking about. Vector is opposite the direction of the velocity vector. The the counterpart to that is when speeding up, the direction of the acceleration vector is the same as the direction of the velocity vector. So everything else except, we'll just fill in the blanks here. I'm gonna write it out, and then you can write it out. I'm not gonna have you watch me write it out. Pause it here. All right, here's the rule. When speeding up, the direction of the acceleration vector is the same as the direction of the velocity vector. How I remember this is I go back to my motion maps. The acceleration vector is going to be helping it go in the same direction as the velocity vector whenever it's speeding up. And that acceleration vector is going to eat away at the other arrow, so it has got to go in the opposite direction when it's slowing down. So the shortcut is concave up, positive acceleration, concave down, negative acceleration. So if we draw these graphs, the positive acceleration one is going to be a positive acceleration, and the negative acceleration one, negative acceleration. In this class, we're only going to focus on parabolas for position versus time graphs, and a parabola is a constant acceleration. A parabola on a position versus time graph is a constant acceleration, and so that's why we have the horizontal lines. All right, that is the end of your graphing notes part 3.